Now it's recording. That's my bad. Hello,
No worries.
YouTube.
Awesome. Yeah, it's so good to be here. Apologies in advance if I stopped to cough. I got sick last week, so I'm still getting over it. But should be fun. I'm really excited. I was so glad to be able to do this and get to present on stuff that I'm really passionate about. So acoustics, really, what is the science and engineering of sound and vibration, and how does that impact your life in a way that you might not be considerate beforehand? And how does it tie in with RF and wireless related technologies? So a little bit about me. I am a third year PhD student in acoustics at Penn State, studying under Dr. Carl Reichard, and I do really fun research into prognostic health management. So I'll be talking about both some wireless stuff and what is acoustics and what is prognostic health management, how does it work with acoustics, and some other fun side projects I thought might be of interest. So before I get too far, I wanted to give a better introduction about myself. So my background is in engineering physics and mechanical engineering. I got a double major in those two from Kettering University in Michigan back in 2021. I really enjoyed the mix of how and why things work from both the in-depth physics and the practical application of the engineering, and really marrying those two together and really getting a broad sense of how things come together in the world around us. And that really got me interested in acoustics because it started to be this perfect combination of getting to both understand math and then see how it actually happened in real life in a really hands-on way, which made it fun for me. So that led me to Penn State, where I'm currently a PhD student. Started out as a master's, I finished that this year, and have started PhD work this fall. So since this is RF Club, I wanted to kind of share first about how I got into acoustics in the first place and STEM, and that really was because of wireless communications. So I've been licensed with my ham radio license. I'm KM4LEO. I've been licensed since 2015 now. Crazy to think about, but had a lot of fun with it. The photo in the middle was operating Morse code with some friends. That's what got me into wireless communications and ham radio in the first place, was just interested in sound and frequencies and how do they work, and wait, you can use Morse code still? Let's do that. So I got my license so I could do Morse code, and that quickly branched out into other things, including satellite communications that tied in my love for space and physics and ham radio too, just taking portable stuff everywhere I could. Um, do that as much as I can, though it's a little bit harder with it being 20 degrees out right now. Um, and then also loving portable operating and doing HF as much as possible. The photo on the left is a portable school club roundup operation from Kettering several years ago. We were in the middle of trying to get our club station still revamped, so some alumni came with a van stuffed full of ham radio equipment and let us operate for a couple of days, which was a lot of fun and was a good way for me to be like, oh, I can take this portably. It's fun. So I love doing ham radio as a hobby and RF and really understanding those frequencies. But as so I got further into my degrees as well, I realized as much as I love ham radio, I wanted to keep that specifically as a hobby, and I wanted to find a career that could use the skills I learned in ham radio and my undergrad degrees and my interest in frequencies in a slightly different way, to be able to do both at the same time. So that really led me to acoustics and led me from really just playing in the high frequency range of things down to the audible spectrum and acoustics. So a lot of the work that I'll be talking about in acoustics really focuses on a lot of these lower frequencies. So infrasound, the human audible sound from 20 hertz to 20 kilohertz. And then there's quite a bit of medical ultrasound, medical acoustics work that happens slightly higher rate above that. And it's not in this particular graph, but there's also elastic waves that travel in solids that are around like 100 kilohertz, that we use for some non-destructive testing as well. So with that little bit of started with introduction to acoustics, let's really dive deep into what it actually is. So like I've kind of hinted at, it's this interdisciplinary science of sound and vibration and how they really interact with the world around us. So it really starts with a core understanding of physics. So how do these waves move in space and time? How is being in a medium affect them? Because unlike radio waves, sound needs a medium to propagate. So it's really starting with a wave equation and then applying all sorts of boundary conditions to it based on whatever application we're interested in. And like I said, there's a different medium, and that sound is going to change as it propagates. So if you want to understand, say, as sound moves from air to water, it's going to bend. Or when you do from water to like a seafloor, if you're trying to image something on the seafloor, understanding how the properties, the physical properties of the system will change a sound. And that's important to know going in. But once you know some of the baseline physics, it's really fun to then apply it to engineering problems. For me, I got into it because of that mechanical engineering background. I got to work on machines, and machines vibrate, machines make noise. So how do you model machines and components as multiple degree of freedom systems? How do you understand this interaction between vibration and sound and how that's going to propagate or bother someone if they're working next to it or cause something to break because it's vibrating so hard? And then, of course, there's quite, like everything else, there's a lot of electrical engineering and circuits that go into it. We have to really understand the transducers. How do they work? How are we actually physically sensing what we're interested in? So how do you model microphones, accelerometers, hydrophones, loudspeakers, the actual concepts and what we need to use to actually gather our data is a key part of understanding the electrical components. And this circuit diagram is a model of a microphone, so modeling it with electrical components so we can have a standardized way of communicating what we're using. So like most engineering disciplines, we have a nationwide organization. For us, that's the Acoustical Society of America. And something cool about it is they've broken down all of acoustics into 14 different technical committees. So this may be a little bit hard to see. My apologies, I couldn't make it bigger. But this is kind of what's called Lindsay's Wheel of Acoustics. So basically starting in the middle with main fundamental physical acoustic concepts and propagating outward to all sorts of topics with earth sciences and like oceanography, life sciences, with medicine, bioacoustics. There's a very big aspect of research into like bioacoustics and focus ultrasound and how do you use acoustics to non-invasively help someone get better. There's a lot of arts in it, so a lot of like music and that sort of thing, as well as quite a bit of engineering, which I'll kind of be more focusing on for this talk, from the electrical, mechanical, architectural, computational, etc. So now that we've kind of got a sense of what acoustics is as a whole, I'm going to do kind of a mile-high rundown on several notable areas of acoustics within this subset, to kind of give you a sense of cool things that we do that might pique your interest. The first thing that I love about acoustics is how practical it is for students who are also interested in wireless communications, like I am and like many of you are. Like we use microphones and headsets every day to get on the air. So how do those microphones and headsets work? How are they designed? How are they made? And who works at the companies that actually makes them for us? That's a huge part of an acoustic engineer's job if that's what you want to focus on. And it's really cool. So you could do it either, from the small scale of home microphone and home radio communications to, as big of a sound engineer for a larger company or like a performance hall, which is a lot of fun. Something that I have been very interested in as well is also like satellite testing. So I believe Rose-Hulman has a small sat team, like many universities. And I don't know how far you guys go in the testing side of it, but there's quite a bit of acoustics that's involved in satellite testing. So wanting to understand the loads that system is going to undergo during launch or during its life. So on the photo on the left is a shaker table, and you can set profiles so you can test loads and try to figure out if it will be able to withstand it or you need to design it differently. The cool thing is you can also use acoustic testing with loudspeakers for satellite work. You can simulate high pressure fluctuations of launch through a bunch of loudspeakers and make sure once again that it'll be able to withstand that high pressure and high fluctuations through that intense time period of its life. A big part of acoustics as well is also architectural engineering. And it's often the one most people think of when I mention that I'm doing acoustics. The first question is, oh, do you play an instrument? And the next is, oh, do you design concert halls? I'm like, no, it sounds fun, but I know about it. So if you've ever been to like an orchestra concert, and really it's interesting to think about how exactly it's made so that you can get the sound. So the sound comes out for the concert hall as a whole like you're expecting. How is that shell behind the orchestra made to redirect sound out to the audience? If you ever looked at the shape of many concert halls, especially newer ones, they're not rectangular because you don't want to get standing waves set up between the walls. You want to keep that what's called flutter echo down so you can hear the music. Um, and like this concert hall in Canada, there's often like diffuse reflectors up on the ceiling, so that sound that bounces, goes up to the ceiling will dissipate and scatter, so it doesn't just like focus in on back on one person and again mess up what they're hearing. You're trying to get an overall balanced sound. I won't go too in depth on the math, but one calculation that we use a lot in architectural engineering is reverberation time. So how long does it take sound to decay by about 60 decibels in a room? And you can tweak that calculation based as you're designing a space to create the sound that you're wanting for a particular space, which is really cool. One thing that I have friends working in is called sound mapping. So how do you take a large variety of data from across a large physical space and use that to understand overall sound levels that can help inform our understanding of animal life, biodiversity, and whatnot in a variety of environments? So this photo here is actually from the National Park Service, and they're very interested in sound mapping and understanding overall sound in all the different parks, so they can, better understand animal life there as they're working on all sorts of preservation in parks. So the photo here is showing just different sound pressure levels across the United States. So I put the equation there for to kind of show you what that equation is. It's decibels, and we're interested. It's a logarithmic scale. It's comparing a measured level that you get from like a microphone with a reference level. This would been in air, so it's 20 micropascals for sound and air. And it's a good visual, like, oh, it makes sense based which locations are noisier based on different cities, but it's good information to have as we try to consider how to help animals and whatnot to live better lives in parks and whatnot. But we're not just interested in sound above ground. We're also interested in quite a bit of ocean acoustics. Um, so there's many, many animals in the ocean, as we all know, and the ones that we know of, there is a very large data set of acoustic data for these animals, so we can understand when we're putting a hydrophone in the water to measured sound, that helps us understand what we're hearing. So the photo on the left is a spectrogram. So it's just a visualization to better see what is happening in sound. So it's frequency versus time, and then that amplitude is the color is the amplitude of the signal, so how loud it is. And this is actually a spectrogram of a dolphin call. So if you had some acoustic data and you plotted spectrograms of it and it matched up, you were able to tell that there is a dolphin in that area. So it's really useful to build up an understanding of what there's so much noise just in the ocean from all the water moving and whatnot. It's good and all ship traffic, so it's important to know what you're looking at, which is helpful. So one cool thing that was done somewhat recently is photo on the right, which is they had an autonomous vehicle that was monitoring with hydrophones in the ocean. And this is like a map of where the vehicle traveled. I don't know exactly why they did this path, but that's what they ended up with. And they've marked locations where they picked up notable frequencies of interest. So using spectrograms, they were able, and similar concepts, they were able to know what frequencies to focus in on based on like what frequencies like dolphins their chirps end up at or whatever. So I thought it was a really cool visualization of how acoustics is able to help us understand an environment that we may not be able to get to personally, in order to better understand what's going on. And of course, I'm interested in acoustics because of mechanical engineering. So I really enjoy doing stuff with noise, vibration, and harshness. So how do you make sure that the large machines that are necessary to in like assembly lines or large companies and large factories aren't harming humans around them with the amount of noise they put off or breaking unnecessarily with all the vibration and whatnot. So the photo on the left is kind of showing some math for calculations that you would do with acoustic materials. So if you have super loud machines, of course you're going to want your earplugs and whatnot, but another good way to reduce the overall noise levels in like a factory environment would be to put them somewhere that also has a lot of acoustic material around it. That's of course a challenge because you don't want to fully enclose it because then you'll have a heat buildup and then something else would break. But it's the balance of trying to reduce some of that sound. So if you have an incident wave of sound from a machine coming into this material, of course, you're going to have some reflect back and you're going to have some reflect forward. And then you can tweak what material you use to absorb as much sound as possible. And one of the calculations we often care about is transmission loss. So trying to get as high of a transmission loss as possible, which means not very much sound power is going out, which is good. There's also a lot of work into vibration reduction and sound isolators. So that machine is vibrating, it's going to transmit vibration from the machine to the floor and then out. And you want to tune some sort of mass spring damper system to get rid of the key frequencies that would do that so that you don't have a lot of parts breaking and vibration you don't want going everywhere. So it's pretty cool. So just as a bit of a reference for people, I kind of wanted to, I really didn't know about acoustics until later in undergrad. So I wanted to provide a little bit of help into, if that's something that you think might be interesting or is fun, just a little bit of reference for what types of places tend to do acoustics research. This is not an exhaustive list by any means, but it's some of the most common universities that I see showing up at Acoustical Society of America conferences. So you can see there's quite a range of locations, and most of them have acoustics as a concentration under some other degree, whether that's a subset of engineering or physics. I ended up at Penn State because it's actually the only civilian school that has a degree specifically in acoustics and specifically for graduate program. I had that broad range of things from undergrad, and I really wanted to focus in on something cool for my graduate degree, so I ended up here at Penn State. So now that you have a bit of a sense of what acoustics is and how it's used, let's go into what I've been doing for research. So I mentioned that I've been finishing up my master's this fall and started my PhD. So I'm going to give you a very abridged version of the work that I was doing for my master's thesis, which was entitled Microelectromechanical System, or MEMS, Sensor Characterization for Diesel Engine Health Monitoring. So we were interested in how do we use acoustics to understand data that we were getting from a diesel truck so we could then use that down the road to predict when it might fail. This can be done in quite a lot of different environments, but of course we're interested in acoustics, so I'll focus on how PHM is used for acoustics work. So diesel engine health monitoring falls under the umbrella of prognostic health management. And PHM specifically is the study of systems to optimize their maintenance and sustainability. So again, how do we take data that we get from a system and use it to have a healthy life, understand a full sense of when that system will and won't be working. So the first part of that is health monitoring. So sensor selection, data collection, signal processing, and diagnostics. There's always a lot of signal processing and computer programming involved in things, which is fun. So for us, for acoustics, we're using accelerometers and microphones. Accelerometers to measure vibration, microphones to measure sound pressure, and gathering data on some sort of system when it's running properly and when it's not, so we can then use that to diagnose damage in a system. For a full PHM project, once you have that health monitoring side, you then employ prognostics to be able to predict the remaining useful life of that system. So if it's like an engine, like I'll go into, how could you use that data to predict when that engine will break? And then finally, the health management part brings it all together in creating workflows for repeatable procedures so it can be done long term. My work specifically is really focused in on the health monitoring side and a lot with the sensor selection, data collection, and whatnot. So in health monitoring, once we decided we were going to do diesel engines, we came up with some research questions. So first of all, can microphones detect the same frequency information as accelerometers? Because accelerometers are very common for rotating machinery because they're small and easy to put on. We just wanted to see if microphones could get some of the same information for prognostic health management. And then we were also really interested in adding in microelectromechanical system or MEMS sensors because they're so much smaller on circuit boards. They're much cheaper to make and they're much easier to integrate with all the other electronics that go into a system. Starting to try to understand what sort of data we're getting from these sensors when some of the documentation is much less for them than standard piezoelectric accelerometers and condenser microphones that have been around for a long time. So the photo here is just kind of showing on a vehicle some of the sensors that we had set up and circled in the appropriate color. So we're interested in diesel engines because they are used across many different applications, whether that's ground vehicles, ships, and whatnot. So we ended up using a long haul vehicle, truck, like was shown on the right, and we were using it for our data. And we chose it because we could easily insert faults into the system. So for example, with an engine, it's very easy. You can insert an engine misfire. So as the engine is going through its cycle, you can make it that the power doesn't go, and then you're able to have a misfire, and that should be detectable by both the accelerometers and the microphones. I won't go fully into the math of how microphones and accelerometers work, but for your reference, just a little bit into the sensors we were using. So these are showing first the condenser microphone on the top and the MEMS microphone below it. Along with just a diagram of how that condenser microphone works. And as that diaphragm of the microphone works, it exerts a voltage, and that voltage is proportional, as the diaphragm moves, sorry, the voltage it exerts is proportional to the sound pressure that's input. And then these photos are showing accelerometers. So we had a piezoelectric accelerometer on the left, and then a MEMS accelerometer next to it. And with the piezoelectric accelerometer, that piezoelectric in the material in the middle, as it is squeezed or expanded, as that proof mass moves, as the whole system moves, you'll get a voltage output that's proportional to its acceleration. So here's a bit of just a visualization of where we ended up putting sensors in the system. We put accelerometers in the engine bay, located far enough away from the engine so they wouldn't have any heat related problems, but close enough we could still pick up the vibration. And then we put the microphones, which were the green and blue boxes, in the engine cab, both because they were easier to insert in the cab when we were sitting there, but also having some sound traveling through the cabin exterior would cut down on a lot of wind noise, so we didn't want to have to deal with. And as a reference, a little bit of the testing that we ended up doing, we were interested in, like I've mentioned, both with and without faults, so we could see how the engine sounded and vibrated, but also idling and driving to get a full sense of a general profile of the vehicle. And this is just showing them the different sensors mounted, the microphones on the left and the accelerometers on the right in the vehicle itself. So once we gathered data on the trucks, got a lot of data on the truck, we wanted to analyze it, do lots of computer work. There was kind of two main analyses that we ended up doing that I thought was interesting that I want to just talk through. The first one was order tracking. So in acoustics, we take data and then we often plot it in the frequency domain to understand the frequencies of the system, which makes sense, do Fourier transform and whatnot. And that's useful for engines because you've got a crankshaft rotating at a very particular engine speed, and you can see that peak show up in the frequency domain along with harmonics of that system. But there's a lot of things moving in an engine, and it's interesting to understand how to it's interesting to know when you're looking at data how signals are related to each other in a spectrum. So one way we do that is through order tracking. So basically, if you have a crankshaft rotating at a particular speed and there's 6 cylinders in it, each cylinder specifically is only going to be firing once every other revolution because a diesel engine cycle takes 2 revolutions to complete for each particular cylinder. But there's 6 of them, so the way they're set up in the engine means that every time a crankshaft rotates with 1 revolution, 3 of those cylinders are going to be firing. So the photo on the right is showing a basic acceleration plot in the time domain with, you can see these peaks in the data. So if you normalize your x-axis, if you get it into the frequency domain and then normalize your x-axis relative to the crankshaft speed, you're then able to get things in the order domain, so you can then see the same what is the word I'm looking for? The same characteristics. Wow, the same characteristics regardless of what speed that crankshaft is actually rotating at. So like an order of 1 would be the crankshaft, and then order of 3 would be another peak you're going to see because 3 cylinders are firing. So I'll show that a little bit more in the data as we get through it. We're also interested in what sort of algorithm can we use to analyze all the data from all the sensors that we could then compare back and forth. And what we ended up using was called the Hilbert transform. So you apply this to a time domain data, and you get a resulting signal that has both real and imaginary components. And those real and imaginary components contain the magnitude, you can get magnitude and phase from them, which is really important because then you can use the phase to get the angle of the system and then be able to figure out what the points where like your shaft is going to be at 0 angle, which means there's another revolution happening. That's interesting because you can back calculate what the how fast your engine is going and what speed you're driving at, which you can then compare between sensors as a quantitative measurement between them. So if this plot is showing a that just phase, the angle plotted, and we circled each of the 0 crossings, so you can both collect the times of 0 crossings to figure out how much time is between when it crosses 0, and then use that to also get an RPM of the system. So one way of doing that is to get that straight RPM so you can compare them to each other. And it's also good because then you know exactly what the speed is and how long it takes for each revolution. And then that'll tell you, that gives you a window of time that you can use to average your data. Because if you get things into the frequency domain and then you average it, you're going to be able to reduce noise and increase the signal to noise ratio, so you can see features more clearly, which is the whole point. We're trying to see, can we see interesting acoustic data for all of these sensors? So once we did that for all the data with both of our all of the data from all of our sensors, we were able to plot them and look at them and compare. So I won't spend too long on it, but wanted to show some of the interesting results that I got from this. So the first thing we were able to see was that these small MEMS sensors were able to get comparable frequency content, especially at low frequencies, right around like the engine shaft speed, and then harmonics of the cylinder firings. So this is a power spectral density, so a measurement of how much power is being output versus frequency. And then I put the order of domain plots on top of that so you can kind of visualize it together. So you can kind of see, regardless of where microphones were set up, we were still able to see key peaks of interest showing up in the spectrums. There was a little bit of amplitude difference between the sensors that we could have been just how the microphones were oriented when they were set up or moved as the vehicle drives and things got vibraty. But the general peaks were showing up the same, which was really cool. But they did die out pretty quickly, and that trends was the same for both types of sensors. And like I mentioned, we could back calculate RPM. So this is a plot of showing that it worked. So the blue plot is the raw tachometer from the truck. So the actual sensor on the truck telling us how fast it was going. And then we took an average version in red to get more of a smooth calculation. And then we put the calculated velocity that we manually calculated from that algorithm on top of it, and was able to see that regardless of which sensor we used, and regardless of if the truck was operating with or without fault, we were able to get a very small difference between the two. So both sensors were working well at back calculating this value. That's useful for PHM analysis because you won't always have a vibration, a tachometer in your truck to be able to tell how fast it's going. So having a secondary way of calculating that is super useful. And then once we were able to apply our windows to the frequency domain data, convert it to the order domain, and then plot it, we were able to see that the power spectrums of the sensors looked very similar, whether they were operating with and without fault when they were idling, which was cool to see. There was that the algorithm was working for the different sensors. This is showing the piezoelectric accelerometers only, but this is true for all the different sensors we looked at. The really fun result that I enjoyed pulling out, though, was that the algorithm was able to pull out data more clearly when the system was actually driving. So the photo on the left is showing microphone data when the truck was driving without a fault. And we were only really able to clearly see this first order peak that was indicating there were cylinders firing. But we should have seen harmonics of that as well. But it was cool when we were driving with the fault, we were able to pick it out much more clearly, which is very useful because that's where the analysis for this work stopped. But if you were doing a full prognostic health management work, you'd want to then use something like this to be able to pick out what are key features in this data that are always showing up that then will definitely tell us there's a fault in the system. Which is a really interesting application of data science that I really hadn't considered before I got into acoustics. So just kind of to wrap up that work, we were able to see that the MEMS sensors were able to detect similar information, regardless of how it was operating. And there was a lot of interesting work that would be fun to do in the future to both expand that analysis, both on the computer programming side as well as the data collection side. But that was my master's work, and I'm done with that now and moving on to PhD work, which is a lot of fun. We're kind of switching gears a little bit, so kind of focusing more on the computer programming side of things and how that implements with acoustics, and how can we use the understanding of acoustic models and acoustics phenomenon and that basic physics and engineering that I've built up over the last couple years. How do we then apply that to some of the hot topics in a lot of industry like machine learning? So how do we compare and contrast different models from machine learning with, for example, models we have for acoustics and understand the differences and improvements between the two? That's challenging with prognostic health management because there's often a lot of, if you, for example, you're measuring data on a real life system like a water pipe, there's going to be, most of the time, it's going to be working properly and there's not going to be a lot of leaks. So it's a challenge for a data analysis trying to understand how do we actually know what we're looking at, which is pretty cool. And then one last real quick thing before I wrap up is kind of talking about a side project that I've been working on that I thought might be of interest because it has some connections with wireless things as well. So as many of us know, there was that total solar eclipse this past year. And there was a lot of data that was collected from a variety of fields, and one of which was acoustics. So trying to understand what we can learn from measurements taken during the total solar eclipse and the effects of the total solar eclipse on nature and how that changed, how the sounds changed before, during, and after the eclipse. So several friends and me, we collected data during the eclipse from Lake Erie, a local state park near Penn State, and also out in Ohio, with a variety of both in totality and not. And we're currently kind of working through that data to try to do both standard acoustic processes and also machine learning processes to kind of get a broad sense of, what animal species were most affected by the eclipse, which frogs are you going to hear the most, etc. How does being in totality versus not really affect areas and sounds? And, how can these observations be the same or different when you're in a natural area like a state park in the middle of nowhere versus an urban area like Milan, Ohio, where I was, and this photo was taken in the middle of a town square where there's a lot of people. And we're interested in sharing that. So how do we package that work so it can be shared with other schools for educational outreach and whatnot? So that's kind of fun stuff that I've been working on. Personally, I really want to combine that with some radio eclipse data down the road as well, because there was so much wireless data taken during the eclipse from various people. It'd be a lot of fun. I'm always interested in trying to find ways to do interdisciplinary topics, especially with RF related things, because both of them are my passions. So yeah, that's a bit of an overview of acoustics and how it's used. A bit of an introduction to applications of wireless related fields that you may not have considered. And stuff that I've been doing recently to both pursue that, both from academically for my degrees and also fun stuff on the side. And like I said, I'm super interested in wireless and acoustics and very interested in doing fun side projects. So if your interest was piqued by anything and are wanting to do anything, let me know. And I'll take any questions that people have.
Guys, can we give Ruth a quick hand? I didn't mention up front, I think Ruth is a pretty prolific person in kind of our ham radio community, and she's been really busy with her PhD recently, so we're really lucky to have her here and sharing her expertise with us. So that's pretty cool. Okay, take a couple of questions. Anyone have anything to ask? Yes.
So yeah, thanks a bunch. So since the total solar eclipse was something that didn't happen much, how do you know that the sounds you reported were actually affected by that, or if they were just like coincidence?
So I guess that is a very, very good question. Part of it would be, so we haven't gotten too far into that far of the analysis, but in terms of making sure they weren't just coincidence, for the small subset that we had, we gathered data before the eclipse started and after to get a smaller subset, but also the data collected at the Black Moshannon State Park. We set up several days before the eclipse, so we have several days of data with nothing happening, normal day and night, no eclipse before and after, as well as the eclipse in the middle to help get some sense of understanding of what's normal and what's not.
Cool, thanks.
Yeah.
Any other questions before we back up? Okay, well, Ruth, thank you so much. This was an awesome talk. I definitely didn't consider basically anything you talked about. So much of this is new to me. It's really cool. So yeah, thanks so much for talking to us. This was awesome. Did we lose her? I think we may have lost her, but oh well. Thanks everybody. If you're part of the club, stick around. It's just gonna be a couple minutes. If you want to be part of the club or you're curious, you can also stick around a couple of minutes and we'll have a quick conversation. But yeah, thanks everybody for coming. Great turnout. Oh, she's back. Hello, thank you.